It is an honor and a pleasure to be here. I'd like to thank my co-author, Jonathan Zahagan, and Dr. Swin from Cal Poly Pomona for their continuous support. Today, I'm going to talk about the design of my sensor network and how it can play a key part in mitigating the impacts of wildfires. Just recently, we have witnessed one of the deadliest wildfires in modern US history, the Maui wildfires, which claimed 115 lives while it lasted. Early detection of wildfires is very important. Wildfires like the Maui and Canadian wildfires can irreversibly damage the environment and can cause immense harm to city infrastructure and people's well-being. In situations where there is a wildfire, traditionally, authorities have relied on people to help detect and report these wildfires to them. This method is low cost and effective in most cases. And when combined with infrared cameras, unmanned aerial vehicles, otherwise known as UAVs, like drones and sensors, it begs the question of why the Maui wildfires were still so devastating in the first place. To answer this question comes down to the cost of employing infrared cameras and unmanned aerial vehicles. 85% of all wildfires are caused by humans, which means that only 15% are caused by natural causes, like lightning strikes, volcanoes, meteors, etc. No matter how good the situation, or no matter how good a solution is, it needs to be implemented in widespread areas in order to actually be truly effective. Our approach of solving this problem comes down to placing sensors in strategic locations in order to detect wildfires where they can most likely happen. The sensors themselves revolve around detecting 4 different variables, being temperature, humidity, barometric pressure, and VOC gas. Temperature and humidity are key factors in identifying if a fire has occurred. Barometric pressure increases and it decreases depending on the type of weather which occurs in the area. Weather patterns like strong winds mixed with dry bushes and low humidity is the perfect recipe for wildfires. VOC gases are produced when wildfires burn materials, which is why VOC gases are a critical indicator of if there is a wildfire nearby. It is an obvious indicator of fire along with temperature and humidity. The system uses an AI detection network to analyze the variables and determine the probability of when a fire can occur. It works in tandem with the application that we've created. The application can be easily installed onto people's phones, and it displays a probability of how likely a fire is to start in their area. It also sends out alerts to people nearby when the wildfire has been detected by the AI algorithm. Here is a picture of the app user interface and where you are able to see the humidity, temperature, gas, and pressure that has been collected from the sensor. Now, the sensors themselves are protected by an outer layer of plastic covering. This allows the sensor to remain cost-effective while still protecting the inner components. It also includes a solar panel, which is attached to the battery, solving the problem of an effective energy source. Now, what separates our sensor from other solutions is the cost effectiveness. Compared to UAVs, which can cost an upward of $400 per hour, the sensors are low in cost and can be used in widespread areas. This has the additional benefit of the consumer being able to afford the sensors, allowing them to protect themselves from wildfires. The detection would allow for early detection of close wildfires, as well as the tracking of the situation of the house after people have evacuated. Other forms of early detection, ranging from video collection, social media detection, and UAVs, while effective in some ways, cannot be used wide scale or are too slow at detecting fires. Sensors can be placed at the most dangerous points where it is most likely to catch fire, and this could definitely help prevent wildfires from spreading into further places. Sensors are also able to cover a lot of ground, as they are $75 per unit, but they allow for communication with other sensors, forming a quick network of nodes, which allows for quick dissemination of information. Of course, challenges exist in the development of any technological solution, and our project is no exception. One critical challenge that we face is the potential for false positives in wildfire detection. While our system is designed to be highly sensitive in order to catch even the faintest trace of wildfires, this sensitivity can also lead to false reports. False positives occur when the system detects a potential wildfire that is not actually present. And this can be a significant concern, as it could lead to unnecessary panic, resource allocation, and disruption to communities. Equally pivotal to the success of our project is the accuracy of the detection algorithm itself. The algorithm serves as the backbone of our entire system, determining whether the conditions observed by sensors truly indicate the presence of a wildfire. In experiment 1, we rigorously evaluated the algorithm's accuracy using a diverse range of wildfire data sources. This comprehensive evaluation included both data obtained from established datasets and data collected during our own fieldwork. The outcome of experiment 1 unveiled valuable insights into the algorithm's performance. The results indicated an average accuracy rate of 80%, a promising achievement in itself. This signifies that our algorithm is capable of accurately detecting wildfires in the majority of scenarios. However, it is important to acknowledge that this is the average accuracy, which also indicates room for improvement, particularly in more complex or challenging scenarios where it's much harder to actually detect the wildfire. The need for further refinement and optimization becomes apparent in the light of these findings. As part of our ongoing efforts, we are dedicated to fine-tuning the algorithm to enhance its performance in challenging conditions. This entails refining the algorithm's decision-making process, incorporating additional variables, and training it with a wider array of data sources to account for various real-world scenarios. Experiment 2 introduced a different dimension to our research, the impact of environmental factors on wildfire spread. In this experiment, we meticulously designed controlled tests that investigate the interplay between key factors such as wind speed, humidity, temperature, and their influence on fire behavior. By conducting controlled burns in test areas with similar vegetation density and topography, we were able to isolate the effects of these individual factors. The results of experiment 2 yielded fascinating insights that enhanced our understanding of the complex dynamics underlying wildfire behavior. It was evident that wind speed plays a pivotal role in fire spread rates, with higher wind speeds correlating to faster propagation. Furthermore, humidity levels emerged as a critical factor influencing fire intensity. Test areas with lower humidity exhibited higher fire intensities, indicating that drier conditions contribute more to intense fires. Additionally, temperature was found to have a significant impact, affecting both the spread rate and intensity of wildfires. These findings significantly enrich our understanding of the variables that contribute to wildfire behavior. They provide a foundation for the future detection strategies by offering a more comprehensive picture of the factors that need to be considered when assessing fire risks. And with this knowledge, we can develop algorithms that not only detect wildfires more accurately, but also take into account the environmental conditions that might influence their behavior. In conclusion, these experiments underscore the multifaceted nature of our project. We recognize the challenges posed by false positives and pivotal roles of algorithm accuracy, driving us to continuously refine and optimize our detection system. Simultaneously, we gain valuable insights into the dynamics of wildfire behavior for experiment 2 insights that will guide the evolution of our detection strategies. Our commitment to addressing these challenges and incorporating these insights ensures that our project remains at the forefront of innovative wildfire detection solutions, contributing to safer and more resilient communities. Comparing our approach with existing methodologies, we also realize the value of aerial platforms and advanced sensors, but acknowledge their cost and potential limitations. Social media's engagement potential is also promising, but lacks reliability in detecting early signs of fire. Similarly, video-based detection offers a supplement, but its continuous video collection can be costly. Looking ahead, our research opens further areas for improvement, and we aim to enhance detection algorithms for even higher accuracy. By equipping sensors with advanced capabilities, we can extend their detection range. Additionally, optimizing communication strategies and collaborating with the emergency services can further enhance our approach. In conclusion, this project offers a promising solution to the critical issue of early wildfire detection, and by utilizing sensor networks, we address the limitations of existing methods, making detection more affordable and accessible. Our aim is to empower individuals, communities, and authorities with the tools they need to take proactive measures in the face of wildfire threats. Thank you for your attention. I'm excited to share my work with you, and my email is on screen, so please do contact me if you have any more questions.